Hello everyone. Today we are going to study electrotherapy. In electrotherapy, one of the topic is ultrasound therapy. It is for the second year students, BPT students. Okay. Now, where the topic is ultrasound therapy. One minute. Ultrasound therapy or UST, you can say ultrasound therapy. Okay, at first we'll go through the definition of ultrasound therapy. Definition. Before going to the definition, we'll go through what is ultrasound. Okay, ultrasound refers to the mechanical vibration. Okay, that vibration which are essentially the same as sound wave, but it has a frequency higher than the audible limit. Understand what is ultrasound? The ultrasound refers to the mechanical vibrations which are essentially the same as the sound wave. Okay, but it has the sound wave has the frequency of audible frequency sound wave. Okay, but ultrasound has the frequency higher than the audible frequency, that is more than the 20,000 hertz. Okay, as such waves are beyond the range of the human hearing, so it is called as the ultrasound or ultrasonic. So normally the ultrasonic frequencies ranges from 20 kilohertz to 10 gigahertz. Okay, ultrasound is a form of acoustic vibration propagated in the form of longitudinal compression waves at frequencies too high to be heard by the human ears. Okay, so now the therapy used through this procedure ultrasound is known as the ultrasound procedure, ultrasound therapy. So what is, you can say, what is ultrasound? Ultrasound or US is an inaudible acoustic high frequency vibration energy which limits or exceeds, one minute, which limits or exceed the upper limit of normal human hearing, that is 20 hertz to 20,000 hertz. That is the normal limit. So what is ultrasound? Is an inaudible acoustic high frequency vibration energy which exceed the upper limit of the normal. You can say ultrasound is a deep heating modalities. Okay, and normally in physiotherapy or PT, the ultrasound ultrasound frequencies used are of 0.75 to 3 megahertz. Okay, so next we'll go to the next para, which is normally next we'll go to the components of ultrasound. Okay, components of ultrasound. First, what are the components of an ultrasound machine? What are the components? First, the component is the main supply. The main supply is the AC current. Okay, main supply is the AC current, normally of 220 volt and having the frequency of 50 hertz. Number 2 is the transformer. Important, you have to write it down step by step. Okay, number 1 is the main supply, which is that AC current supply, normally of 220 volt and having the frequency of 50 hertz. Next is the transformer. The transformer, here it is a step up transformer is used to increase the voltage of the current. Okay, the current now flows from transformer to rectifier. Okay, next number 3 will the component will be the rectifier. In the rectifier the current is converted. Here you have to notice about this point. What is the function of the transformer? Here the current is converted from AC to DC current. Then the current flows to the amplifier. Okay, in between amplifier and rectifier there is oscillator. The purpose of the oscillator is to give high frequency oscillating current. to the output circuit, which then flows to the amplifier. Okay. Next, number 5 point is the amplifier. The purpose of increasing the magnitude of the current is called amplification. Amplification. The purpose of increasing the magnitude of the current is called as the amplification. The current then flows to the coaxial cable. Number 6 is the coaxial cable. What is the coaxial cable? It is the simple wire covered by a metallic plate which runs parallel to the wire and separated by insulating material. It takes the current to the transducer or ultrasound head. The transducer is also known as the ultrasound head. So these are the components of ultrasound production, or when we will go to the production in the next phase. So these are the components of ultrasound. Next we'll go to the production phase. So here are the parts of the component or components of the components. This is the main supply. The main supply is here, or power supply. Then the power supply, the current goes, the main supply normally is of AC current, okay, which is of 220 volt and 50 hertz frequency. Okay. Next, the current from the main supply, it goes to the transformer, where a step up transformer is used. Step up transformer is used, which increases the voltage, increase the voltage. Okay. Next, the current then flows to the rectifier. Where the current is converted from AC to DC. AC to DC, where the current is converted. Okay. After conversion, the current flows to the oscillator. The oscillator. The function of the oscillator is to give the high frequency oscillating current. Okay, high frequency oscillating current. Then it goes to the amplifier. Okay, the amplifier function is to increase the magnitude, of the current. That is called as, known as the amplification. Okay, after amplifier, the current goes to the coaxial cable. So this is the coaxial cable. The coaxial cable is a simple wire, okay, covered by the metallic plate, which runs parallel to the wire by the separate insulated material, and it takes the currents to the transducer. So this is the transducer hole, okay. This is the transducer, okay. Before drawing the component, you will have to draw this in the exam. When you are writing the components of the ultrasound, you have to draw this picture or schematic picture for the next. Before going to the production of ultrasound, we have missed one point about the components. It's number 7 component is the transducer. The transducer, okay. The transducer here, component under the components. Number 7 point is the transducer or head of ultrasound head, that is known as the ultrasound head. Or US head. So most frequently in the exam, 5 marks question is asked about this transducer or ultrasound head, okay. So what is the transducer? Firstly, we'll know what is the transducer. Transducer is a device that converts energy from one type to another. Like you can say, it converts electric energy to sound energy. Electric energy to sound energy. Okay. And it may be vice versa. Next, Now in case of ultrasound transducer, ultrasound transducer, it converts the electric energy into mechanical sound waves. By changing its thickness, that is known as the mechanical deformation. Okay, next it is the transducer is made of piezo electric crystal. Transducer is made up of piezoelectric crystal that is of 2 to 3 millimeter in thickness. That is made of quartz. The transducer head is made of piezoelectric crystal that is made of the quartz crystal or synthetic ceramic crystal that is lead zinconate titanate or barium titanate. So this is the schematic diagram of the transducer. Okay, in exam you have to draw this schematic diagram. You can also draw like in short. can say this is the coaxial cable. This one is piezoelectric crystal. This is one is this portion metallic front plate. This one is resonating coil. This is insulator. It is metal housing. Next we'll go to the production of ultrasound. The ultrasound wave are the sound wave which cannot be heard above 1 megahertz, and the sound wave which can be heard by the human ears are called audio waves. Okay, next, when the electrical potential is applied, okay, at first you have to write it sequentially, such as electrical potential is applied on the quartz or barium titanate or zinconate, that is the quartz crystal of a specific size. Okay, at first electrical potential is applied on the quartz or barium titanate. Production electrical potential is applied on the quartz crystal, that is either made up of barium titanate or lead zinconate, which may be of specific size. Okay, after applying this, what happens? Applying this, there is, it starts vibrating. What? The transducer or ultrasound head starts vibrating and produces sound. Okay, if the potential is increased, the sound cannot be heard, and thus ultrasound is produced. So this is known as the piezoelectric phenomenon. The phenomenon is used in both diagnostic and therapeutic ultrasound machines. Okay, so this is the piezoelectric phenomenon. And what is the piezoelectric effect? There are two forms of piezoelectric effect. One is direct, another is reverse piezoelectric, or it is indirect. So another important topic which comes for 5 marks question is piezoelectric effect. 5 marks short note question comes from this. Okay, so what will be this? Piezoelectricity is the ability of some crystal to change their thickness in response to passing an alternating electric current through them. Okay, so next, there are two types of piezoelectricity. One is direct piezoelectricity. What is direct piezoelectricity? Is the generation of an alternating electric current on the crystal when compressed. And number 2 is indirect piezoelectricity, or it is also known as reverse piezoelectric effect. Piezoelectric effect, also known as the reverse piezoelectric effect. What is this? Is the change of crystal thickness that is compression and rarefaction. When an AC current pass through the crystal, this reverse piezoelectric effect is used to generate ultrasound at the desired frequency. Okay. The direct piezoelectric effect, the generation of an electrical voltage across a crystal when the crystal is compressed, only compression. If the crystal is expanded instead of compressed, a voltage of opposite polarity is induced. So only compression produces the direct piezoelectric effect. Direct, only compression. Okay, but in case of reverse piezoelectric effect, the contraction or expansion both occurs in the crystal. This is contraction and this rarefaction. This is contraction and this is rarefaction. Both occurs in the crystal in response to a voltage applied across the phase. A change in the polarity of the applied voltage caused contracted crystal to expand and vice versa. The alternating voltage makes the crystal vibrate at a frequency of the electrical oscillation. In this manner, a piezoelectric crystal can be used to generate ultrasound at any desired frequency. Okay, so ultrasound normally purposefully used through this reverse piezoelectric effect. Okay, through compression and rarefaction. What? Compression and rarefaction. So this is the compression and rarefaction. Here this is the transducer or ultrasound head. From here, this portion is the compression and this portion is the rarefaction. Again, then compression, then again rarefaction. Again, this sequentially goes and goes and goes. So this is the compression rarefaction waves of ultrasound produced due to the reverse piezoelectric effect. Okay, and now we'll go to the medical frequencies of ultrasound. What are the medical frequencies? Normally in the physiotherapy equipment, it is of 0.75 to 3 megahertz normally, and in the diagnostic equipment it is 1 megahertz to 10 megahertz it is used. For surgical equipment it is 1 megahertz to 5 megahertz. Okay, Next we'll go to the propagation and speed of ultrasound. Propagation and speed of ultrasound wave. Normally, human body possesses a characteristic resistance against the propagation of ultrasound. Each tissue in the body has a characteristic impedance, that is denotes the Z, and the impedance is directly proportional to the velocity of the propagation and the density of the tissue, directly proportional. Z is equal to PV. The velocity of the ultrasound through some media are in the air, it is 344 milli per second. In water it is 1410 milli per second, and in muscle it is 1540 milli per second. Okay, next go to the transmission of ultrasound and the ultrasound field. The beam of the ultrasound emitted from the transducer, the beam which is emitted from the transducer is not propagated uniformly. Okay, the beam from the transducer head, this is a so-called transducer head. The beam which is produced from it is not propagated uniformly. Okay, when emitted from the different places in the face of the transducer, travels to some point in space in front of the transducer face along with the different path, hence remain out of phase. Some waves cancel each other, whereas other reinforces, resulting in an irregular pattern of sonic wave close to the transducer phase, that is called as the near field. This is important. The near field or Fresnel zone. That is near field or Fresnel zone. Okay, and where as beyond the near field, away from the transducer head, there exists the far field, that is also known as the far field or Fraunhofer zone. Okay, so this from here, the transducer head generator, this is the near field, this is the far field, Fresnel zone and Fraunhofer zone. This is Fresnel zone, near field, this is Fraunhofer zone, that is the far field. In exam, somehow the ultrasound beam question comes about the near field and far field. Near field or Fresnel zone and far field Fraunhofer zone, that Fraunhofer zone. This 5 marks question short note comes regularly from this Fresnel zone and Fraunhofer zone. Next we'll go to the effective radiation area or ERA. What is the effective radiation area of ultrasound? It is the area of the transducer from which the ultrasound energy radiates. Okay, ERA is the area of the transducer from which the ultrasound energy radiates. Because the crystal does not vibrate uniformly, the ERA always smaller than the area of the transducer head. So this is not, this is the transducer. The crystal does not vibrate. Here is the crystal. It does not vibrate uniformly. That's why the ERA is here. The ERA is produced. This from here to here is the crystal area. So that's why the ERA will be smaller from here to here only. ERA will be smaller than the transducer, the area of the transducer here. The ERA should be taken into consideration while calculating the extent of the near field. Okay. Now here are the length of near field for ultrasound of different frequency with transducer of different sizes. So the transducer side is 1 centimeter radius per centimeter. The length of the near field corresponding to the frequency. When there is 0.75 frequency, the near field will be 5 centimeter. When there is 1 megahertz frequency, it is 6.7. When there is 1.5 megahertz, it is 10 centimeter. And when there is 3 megahertz, it will be the near field will be of 20 centimeter. Okay. Next we'll go to the modes of ultrasound. The ultrasound can be applied either on continuous mode or in the pulse mode. One is continuous mode, one is pulse mode. In continuous mode, there is continuous delivery of ultrasound throughout the treatment period. This mode is primarily used for thermal effect in the tissue. And another one is pulse mode. In this delivery of ultrasound, only a portion of the treatment period. Delivery of ultrasound is pulse off, on and off throughout the treatment period, producing more of mechanical or non-thermal effect. In continuous, there will be thermal effect. In pulse mode, there will be non-thermal effect than the thermal effect. The proportion of the total treatment time of the ultrasound is expressed as the mark is to space ratio, or that is known as the duty cycle. The duty cycle and mark space ratio here. This also 5 marks questions come from this short note, duty cycle or mark space ratio. Before going to the mark space ratio or duty cycle, we'll go through the thermal or non-thermal effect. What is thermal effect, non-thermal effect? It is the we'll go through the physiological effect of ultrasound. Physiological effect of ultrasound. Under physiological effect, there is thermal effect, another one is non-thermal effect. It is 10 marks question, important for exam. In our next video, we'll go through the physiological effect of the ultrasound and as well as the indication, contraindication, modes of applications, potential dangers using ultrasound. It will be in our next video. Thank you for today.